For the introduction, and thank you for the invitation. It's a pleasure to speak. And just 1 second, I will share my slides. So I hope you can see my slides. Okay, so let's start with the general setting. So we consider a complex manifold X together with a proper holomorphic submersion to another complex manifold S. And additionally, we have an holomorphic line bundle L on the total space X. Yeah, and we would like to study the geometry of this this vibration here, this family of complex manifolds. And whenever you want to study this geometry, a good idea is to look at a relative canonical bundle of this family. Yeah, this is this object here, K X over S, which is just defined by the canonical on the upstairs on the total space minus the pullback of the canonical bundle downstairs, dual minus 1, and so this is the relative canonical bundle, which appeared in the title of my talk. And its property is when you restrict it to a fiber XS, so XS is just here a fiber of this vibration, small s in capital S, you get a canonical bundle of this fiber. Yeah, this is a complex manifold. And the positivity properties of this relative canonical bundle somehow reflect the geometry of this vibration. Yeah? And for instance, you could measure the positivity of this of the canonical bundle by looking at its space of global sections, which is H0 XS of canonical bundle XS. And to allow for more flexibility for in applications, we twist it by L, yeah? Restricted to XS. And these are finite dimensional vector spaces, and they form generically a vector bundle, which is the push forward of K relative X over S times L. Yeah, and this is the direct image sheaf we will consider here in this talk. And the first statement in this direction is the result of Berndtson, which says that this direct image is first, it's locally free and has some positivity properties as a vector bundle, so it's semi-positive, respectively positive, if L is so. So this means the positivity of L is inherited to the direct image. Yeah, and the property of being locally free, this just comes from Ozawa-Takegoshi extension theory, from the positivity of L. Yeah? And so what is meant by this positivity? So there's a metric actually on this push forward on this direct image, natural metric, which is just the L2 metric on this space, and which I will explain more precisely in a few minutes. Yeah, and the good thing is it comes with a precise intrinsic curvature formula in the case L is strictly positive on the fibers. Yeah? For instance, if L itself is ample, so we have a really a nice curvature formula that allows for a nice geometric interpretation. Yeah? And shortly after, this result was generalized to a more singular situation. So maybe first we look at a very direct application of Berndson's result to get a feeling what's the use of this. For this, we consider a family such that the total space is Fano. Let's say everything is compact here, and then we can relatively easy prove that a base is also Fano by just plugging in L as the anti-canonical of the total space. Yeah, and this Berndson's result directly gives that minus Ks is also positive. So that this means that S is also Fano. This is just a very direct application of this result. So, and then there's a generalization to a more singular version. So like what you need in algebraic geometry when L is merely pseudo-effective. Yeah. So it comes with a singular Hermitian metric H that whose curvature current is semi-positive. And then the statement is that there's also some positivity, yeah? But now you have to consider the correct subsheaf, and this is here just the subsheaf here on the left. It's just the L2 sections, yeah. So you need to consider the L2 sections. And for those, you can define in a reasonable sense, the L2 metric. And there, for this, you get also some weaker positivity result. Yeah, they introduced the notion of singular Hermitian metric on a vector bundle. And in this sense, it's positive in this singular sense of Griffiths. Yeah. And here, so this question is of this positivity in general of direct images is closely related to positivity of the pluricanonical itself. For instance, what you do here is, I mean, what is L in typical applications? L is, you just write this as an adjoint line bundle, yeah. Okay, X over S times M minus S times Kx over S. And this is a typical example of our L. Yeah? So this is closely related to positivity properties of the pluricanonical itself. And the caveat here is that in this singular situation, there's in general there's no curvature formula that allows the geometric interpretation. Yeah? But this is actually what you would like to have, because for instance you would like to characterize the situation when the metric on the direct image is flat. Yeah, so in the smooth case, in the classical Berndtson situation, when the L is relatively ample, then you could say, for instance, if the direct image is flat, then the family is locally trivial. And so you can identify fibers, and moreover, you can also identify the metric on these the metric on L on the fibers. Yeah, this is would be important for questions in algebraic geometry. So, for instance, so the main motivation of this studying these direct images comes from the famous Ithaka conjecture in birational geometry. So here you consider a so-called algebraic fiber space. X and Y are non-singular projective, and F is only surjective with connected fibers. So you even drop the condition of that F is submersive, and then you expect this inequality for the Kodaira dimensions. Yeah, and kappa X over Y is here the Kodaira dimension of a general fiber. And a major achievement in this direction was made by Zhao and Paun, who were able to prove this conjecture in case the base is in abelian variety. And the main ingredients for this were just positivity properties of the canonical bundle. Yeah? So the main ingredients here, positivity of the pluri-relative canonical and its push forward. So far for the history. So our aim here is really to make progress on the curvature formula in a singular situation for this metric on the direct image, and maybe the first, the easiest singular situation, or the mild singular situation, is the Poincaré typesetting. Now we take our F over submersion, proper holomorphic submersion F as before, and now we introduce we have additionally a divisor curly D on the total space, which for which we require it to be relatively SNC, relatively SNC. By this we mean that when we restrict it to each fiber XS, then it should also be an SNC divisor. And to introduce some notation, we denote the open fiber XS minus the divisor just by XS prime. So these are the open, is the open part. And then, as before, we consider a Hermitian holomorphic line bundle on the total space, such with so in general H is a singular Hermitian metric which is smooth on the complement of this divisor, and along the divisor we require the following asymptotic behavior. So note that we write here for the left-hand side here we describe the inverse of the metric. So for the inverse, we have this expression and the object, what is meant by this. Well, first, H the infinity is just the ordinary smooth metric on L inverse. So it's smooth on everywhere on the total space. Just yeah, to compare it to this singular metric. And then in the denominator, this is the expression, that's the Poincaré type expression that we recover here. So sigma I is just the section cutting out this component of the divisor D, this component Di, and we measure it with respect to a smooth metric Hi. Yeah, on this component Di. Then we, on the inverse, we just get this Poincaré type expression. Yeah, so note, so the inverse has Poincaré singularities. The original metric has zeros, in a Poincaré type zeros along the divisor D. Yeah, and the motivation for this comes later from the log canonical polarized case. So this definition is modeled after this case, which we will see later. So okay, in U, so this is maybe this is just to cover this application I will present later. This is some function which is lies in fiberwise in some Hölder space with respect to quasi coordinates on these open fibers, and together with some regularity in the horizontal direction. And by this we mean that it's Fréchet differentiable. So for the moment we can just ignore it, and it won't play really a role here for my talk. So just add it to 1, yeah. But it has to be there just to cover this application. And then additionally, I have to require that when I look at this metric and I compute the curvature of this metric along each fiber, then I get some form which I call omega s. This I require to be a Poincaré type Kähler-Einstein, just a Poincaré type Kähler metric on each open fiber. Yeah, so it doesn't come directly out of this asymptotic behavior expression, because in principle this x bu could offset this this Poincaré type expression in the denominator. For instance, it would be automatically of this Poincaré type form, this omega s, if this x pu is just 1, yeah, or it's just a smooth, it's just a constant, yeah. But because I have this x pu here, I have to require this, yeah. But yeah, in the application, this will also automatically be the case. Okay, maybe let's just explain a bit more about this Poincaré behavior on the next slide. So I computed the curvature on each fiber. So we could as well just compute the curvature on the total space. And then I denote this form by omega x prime. So it's just this is the form where it's this is the expression where this form is really smooth on this open part of the total space. And then I look for it. Maybe I would like to see what is was it meant by or just to recall what is a Poincaré type metric. And for this, I take some holomorphic coordinates, z1 up to zn. So n, it should be the dimension of the fibers, and s is a coordinate along the in the base direction. And together they form a system of coordinates on the total space. And with respect to these, the divisor d, which is supposed to be s and c, is given just as a union of hyperplanes. And then I can write down this Poincaré type scalar metric on the open fibers, omega s, just in this usual form. It's quasi-isometric to this Poincaré type model metric. Yeah? So just to recall what was meant by Poincaré type metric. So this metric, the scalar metric, has poles along the divisor, and recall the metric on H has Poincaré type zeros along the divisor D. Okay, and this implies in particular, because I require the omega s to be scalar forms on this open fibers, that L times D is relatively big in F. So so remember, so this is now relatively, so this is now on the compact fibers, and the reason is because I take the metric H on L, and I take the canonical singular metric on D, and this cancels out, so to speak, the heavily singular part in L. And because when I take the curvature of a Poincaré type metric, this is going to produce the curvature current along the divisor, or it's minus the curvature current. This is just offset by adding this D. And then in this way, I get a singular metric on L times D, whose curvature is the scalar current with which has vanishingly long number. And that's the reason why it's relatively big in F. Okay, and to wrap this up, this definition for this, or this hypothesis on this metric H, just say that the inverse has Poincaré type singularities along the divisor D. Okay, so far for the Poincaré type setting, and then we are concerned with the correct space of sections we have to look at for our for the fibers of our direct image. And as before, we have to look at some space of global holomorphic sections. So this time we look at, of course, we are interested at the end in the L2 metric, so we have to look at the L2 integrable holomorphic endforms with values in L. Yeah, to indicate this, I have this index 2 here, so these are the L2 holomorphic sections. And it turns out in this Poincaré type setting, this can be identified. Yeah, so you can do it, compute it directly, or just refer to work of Saka and Fujiki, that this can be identified with the holomorphic sections on the compact fiber, which have log poles along the divisor. So the reason, of course, when you allow zeros for the metric, you could allow poles for the sections. Yeah? So omega n log d is just a bundle of logarithmic n forms with log poles along ds. So you have just two different notations. So it's omega n log d or k times d. Yeah, it's just a different notation. And this is good news, of course, because now you can identify your L2 space on this open fiber with sheaf cohomology of a even locally free sheaf on the compact fiber. In particular, it's finite dimensional. Yeah? So, and more globally, we can make this identification on the total space. Yeah, so the sheaf of holomorphic and L2 integrable sections of K relative tensor L can be identified with the bundle of logarithmic relative n forms or relative logarithmic n forms with log poles along D twisted by L. Yeah? So this can be made can be formulated on the global level. Okay, so far this is so now we know what space to study, and we restrict ourselves to the set where the dimension of this space is constant. So this means you should exclude some analytic subset of S, or we assume from the beginning on that the dimension of the space is constant on S. And this means that this is the direct image we should look at. So this is the vector bundle on S. So this is now our direct image that we can study by those in this setting. Okay, and then how can we represent sections of this setting? So a section, a holomorphic section of this push forward is just given by a logarithmic n form on the, yeah, it's just a section of this tensor bundle here. So it's in the abstract sense, which restricts to each fiber to a logarithmic n form with values in L. Yeah, and by the previous identification, we know that its restriction is L2 on each fiber, so on each open fiber. And this allows us to define the natural L2 metric just by multiplying those pointwise and integrating along the open fiber. So for the last equation here, so here for the last equation, I used the Hodge-Riemann bilinear relation to replace this. But this is dot means it's really a dot with respect to this metric H. And here, so this is going to appear here, but now the whole thing becomes independent of this. So there's no Kähler form anymore here, because you have here a 0 form, cup 0n form, and that's a 0n form. And that's going to be an n form, so that you can integrate. Of course, it's somehow L-valued, so this you can contract by measuring it with respect to this metric H. Yeah. Okay. So then, what can we do? Okay, so I mentioned that we are interested in somehow in an intrinsic curvature formula. What is meant by this? It's a formula that allows for a geometric interpretation. And so this formula will contain some objects that I'm introducing now. So for implicity, as is the basis one-dimensional to make just the notation easier. And then we take a tangent vector on the base. And we want to describe the Curvature map of this family. Yeah? So this is measuring the infinitesimal variation of the fibers. And in this form, as I've written here, as this goes to this space of L2 integrable sections, it's actually measuring the infinitesimal deformation of the pair, of the logarithmic pair, and xs comma ds. Yeah, so it's not just the deformation of the compact fibers; it's really the deformation of the pair xs comma ds. Yeah. That's the right space to look at. Can be identified with h1 of xs, and then it's tx as minus log d. So this is this is just here if you take the logarithmic one forms, and then it's just a dual of it. It's just a dual of it. Yeah, this is the right space for that is the space that parameterizes this deformations of smooth logarithmic pairs. And the question is, how can we describe it in this, given our metric, our situation, and also our metrics. And for this, we just look at this canonical sequence here, and the Curvature map is then the edge connecting edge homomorphism of the long exact cohomology sequence, and the metric or the one-form form omega x that I introduced at the beginning was the curvature of the metric small h. That allows for a canonical splitting of this sequence, and in turn this allows for describing this edge homomorphism, the Curvature map, in the following way. So we have to lift this tangent vector ds, and we lift it in such a way that the lift is horizontal with respect to each fiber. Yeah, so it's horizontal. So the inner product is 0 with all tangent vectors that come from the relative tangent sheaf. Yeah, so this is the horizontal lift of this tangent vector, and this plays a central role in all the curvature computations that were prior to this work already in all these curvature computations in the compact case, and also in Berndstson's intrinsic formula. So it goes back at the end to Theo, who studied the curvature of the Weil-Petersen metric on the Teichmann space. Okay, so this horizontal lift, from this we derive our two intrinsic objects that are going to appear in the curvature formula. The first one is the Curvature form. So this is just now we take the d bar of this horizontal lift. This is now a 0,1 form with values in the tangent bundle, and it turns out in this setting that's also L2. Yeah? So this has to be proven, of course, but this turns out. And the next thing is the so-called geodesic curvature, which I denote by phi here, and it's just a function on the total space, and just the inner product of this horizontal lift measured with respect to our 1,1 form omega x prime. Yeah? So omega vs is living on the open, on x prime, and I measure it with respect to this omega x prime. And the interpretation for this is just the measuring because I have this relation. So if I take the top power of this omega x prime, which is n, the power is n+1, it's the dimension of curly x, and then I get this expression, and I know, okay, my assumption was that the metric is relatively positive, so it's positive along the fibers. So then I have this relative volume form omega x prime over s to the n. So this is positive, and phi is, so to speak, the eigenvalue in the horizontal direction. So I get the line bundle L. So it's on x prime. It's strictly positive if and only if this function phi is strictly positive. Yeah. So phi is really measuring now. The positivity of L is really condensed now in this function phi because of my assumption that it's already positive along the fibers. And now this allows to formulate the main result, the curvature formula. Now, given our family of smooth log pairs and this Hermitian line bundle L with, as you described above, so that its inverse has Poincaré type singularities, or in other words, H has Poincaré type zeros, then I consider the curvature theta of this L2 metric I just described on this direct image here. And what is the curvature? So the curvature is the endomorphism valued 1-1 form. So I can apply it to a section and pair it with a section. So I apply to the typical section psi, and I pair it with a section. So what I get is a 1-1 form on the base. The base is one-dimensional, so this is just the same as a function. And this has the following expression. So this is the integral over this fiber. So this just take the inner product of this, so the inner product of phi with itself. And so the L2 norm, but this is multiplied with this geodesic curvature phi. Yeah, and this is just a function that I can integrate with respect to this volume form I have. And the second term is the one where the Cordell-Spencer form is showing up. So I have somehow a cup product with the Cordell-Spencer form. So the Cordell-Spencer form, remember, is the 1-0 form with values in Tx. So I can contract, and psi on the fibers, the section psi is the n0 form. So I can contract with the tangent space, with the vector weight space, with the vector field part of A, and I can wedge with the form part. Yeah, what I get, A cup psi, maybe I should annotate this. This is now this is n-1 form with, of course, L valued. And so there you should think of it as this. So you apply this this inverse of this Laplacian here plus 1, and then you take the point was inner product with this, with respect to this H, of course, the point was inner product with the second part, yeah, and then you integrate it, and that's it, yeah, that's the expression for the curvature, and so the only showing the intrinsic object is this geodesic curvature phi and the Cordell-Spencer forms A. Yeah? That's just the same expression as in the compact case. Yeah? It's just the same. And the point here is that so psi is when L is semi-positive, this means that psi is of course semi-positive on the total space. So the first thing is semi-positive, and the Laplacian is of course a positive operator. So this is also it's even a strictly positive operator. Of course, in principle, this A could be this could be 0, yeah. But in any case, each term is semi-positive here. So this is so the upshot of this is, so this direct image is Nakano semi-positive if L is so. Yeah? If L is semi-positive on this total space and positive along the fiber. So this is just the analog of Berndson's result. But of course, with the additional part that we have in the direct image, we twist with this this effective divisor D, because these are exactly the two integrable sections. Yeah, because the metric has zeros, so we can allow for poles for the sections. Okay, then what's the application for this result here? So the main field of application is here the case of logarithmic canonical polarized pairs. And what is meant by this? So we consider this family F together with this divisor effective relative SNC divisor D on the total space, and we have this smooth family of log pairs as before, XS, DS, and we call it log canonically polarized if KXS plus DS is ample. Yeah? So that's the condition here in this application, and in this case we have this on each fiber the unique complete Poincaré type killer Einstein metric on the open fiber XS prime. And this is just with a Ricci curvature -1, so given by the work of Kobayashi and Tian and Yao. And this family of metrics induces a family of volume forms, a smoothly varying family of volume forms on the open fibers, and they in turn induce a metric on. This can be read as a metric on the relative canonical bundle on the total space. And this is going to be to play the role of L here in this application. And in this context, so the curvature formula says that we have a sign for the curvature of the L2 metric if L has some curvature sign. Yeah? And first, we need in this application we need to say something about the positivity of L equipped with this metric coming from the Killer-Einstein forms, and the result in this direction is that it's just the analog from the compact case. So so the curvature of this Hermitian metric on this L, which is the relative canonical, this curvature is semi-positive, and if the family is effectively parametrized, which means that this Cordero-Spencer map I introduced before is injective in each point, then it's even strictly positive. Yeah? And this is just the analog of Schumacher's result from the compact case, and the proof is also just analog, more or less. So it's an application of Yao's almost maximum principle in the complete case. Yeah? This gives just this result, and now this allows that we can apply our main result to this setting here, to the setting of logarithmic canonically polarized pairs, and we get as corollaries that for this smooth family. So this is just first a corollary of the second theorem. It's just to state it in another way. So this was stated on the X prime, so where everything is smooth. But now, what does it mean for the compact, for the relative canonical on the compact space? As before at the beginning, I said something. Okay, when this means that something, when I add D, this is then relatively big in F, and the same thing applies here. So when I consider this setting on the total space X without removing the divisor and then multiplying by D, I get that this is nav in the general case, and if it's effectively parametrized, it is even big. Yeah, so this one is big, and this is also yeah. So yeah, in principle, Berndtsson's bigness criteria, because you have a metric which with vanishing long numbers here. And yeah, the form of the Poincaré type metric means means that you to offset this term with gives curvature current, you have to multiply by this d equipped with the canonical singular metric coming from a section. Okay, and then in the last step we could put this together and or apply this to the main, plug this in the main and in the main result in the curvature formula, and then we get that in this situation we really get a sign for the curvature of the direct image, and the direct image in this case has the form you take, so L is the relative canonical, and so you get it twice, and you have to add this d here. Yeah? You have to, in this situation you have to add this effective divisor d. Okay, so far for the results, maybe a few words about just one slide about computation. So we want to make the computation carry over from the compact case carry over to this L2 open case. For this, the main thing is that you can that all the integrals exist that you are computing. So you need to check at each step that all the integrals exist. And computing curvature means you need to take derivatives twice. So here's one derivative. So you need to take derivatives of this L2 metric, which are fiber integrals. And for this, to start this computation, you need to know how can you differentiate this fiber integrals in the base direction. This is done by using Lie derivatives of the integrand, and this is the Lie derivative in the direction of this horizontal lift. Yeah? This is one justification of using this horizontal lift, because then you get this lemma here. Okay, this lemma is valid for an arbitrary lift of the vector field. And yeah, but the next one, so this, what in the first lemma is this abstract eta, is in our case for the L2 metric, it's the inner product of two sections, or the L2 norm of just one section psi, and to split it off, you to make it split off, you need here that it's really a horizontal, it's a horizontal lift, yeah. Because with respect to a horizontal lift, here with respect to a horizontal lift, the L2 derivative and not the Lie derivative with respect to the horizontal lift v of the metric of omega s is 0. And this allows to split off this inner product here. So you don't get a contribution from the metric here, or from h or something. So remember, omega s is minus I dd bar of log h. So everything comes from h, and these are therefore closely related. And yeah, this condition, and v is derived from omega s here, or is derived from omega on the total space. So everything comes at the end from the metric. Yeah. Okay. Good. And then yeah, another application would be, so this is the last application. Beside this main application, I showed this case of log canonically polarized pairs. Maybe there's another idea how to apply this. So this is the case when you have a big line bundle on the total space. So we consider again a relative setting, this family, and a big line bundle on a total space which has such a decomposition, so it's written as it's ample plus effective. And so this effective E is now what was before over D, and has components EI, and it's again, it needs to be a relative SNC, and A is an ample line bundle together with a positive metric HA. Yeah? And then we modify this metric on the ample line bundle by make it artificially of Poincaré type as needed to apply our result. So for this we multiply it by this additional term here that comes from the norms of this sections sigma I, cutting out these components of the divisor E, these EIs, and measured with respect to a smooth metric HI, as we've seen before in the definition of this asymptotic behavior of this metric H. And here some epsilon would be enough, some epsilon bigger than 0, because so 1 is not needed, just some amount of this Poincaré type behavior, so Poincaré type zeros along the divisor. And then to apply this, we need some positivity. So our requirement here is that also this modified metric has still some positivity. Yeah? This in general, of course, we cannot expect, because so in general, in this situation, maybe X is the base S is maybe not compact. So in the compact case, we could of course achieve this, but maybe in some quasi-projective situation, when maybe S has some compactification or something, yeah? Then maybe we would be able to arrange this. But this is our additional assumption here, that also this modified metric has still this positive curvature, and then we equip F. So F is still this big line bundle A plus E, and then we equip F with the product metric, this modified metric HA epsilon times the canonical singular metric on this effective divisor E, and then we observe, okay, this A together equipped with this modified metric fulfills the requirements of our main theorem. So we apply the main theorem now not to F, instead to A, and what we get is that this direct image has the L2 metric on it has a sign, has positive curvature. Yeah? It's Nakano positive. So this was a part of the result, that the L2 metric on the direct image is really a smooth metric now, and we can really speak of Nakano positivity in the usual sense, yeah? Not in some singular sense, really in the ordinary sense. And if we compare this to the Berndtsson-Paun result, if we instead would apply Berndtsson-Paun to this situation, say directly, so the benefit here is that we get back, so the benefit here is that we get back here this, we applied to A, but we get back this, we get additionally this E and end up with LF, which where we are interested maybe in the beginning. Yeah, this is the big line bundle. So now we are interested. We have a situation where the adjoint is the twist of the adjoint bundle is the twist is with some big bundle, and this is we get this F because we can add this E here. Yeah, and if we instead would apply Berndtsson and Paun directly to this F here, equipped with the natural metric, which is just HA times the singular metric on E, we would only get, so the multiplier ideal sheaf here is O minus E, yeah, because the singular part comes from E, and here we have the singular metric is given by a section, and the multiply ideal sheaf is here just O minus E, which is removing E from the formula, and we just end up here with we would just end up here with this this expression here, and this is, of course, this is just only a subbundle of the one which we are interested in, maybe this this F here. Yeah. And this is then, this has now the form here, this has the form of the classical Berndtson result. So we applied the singular version, but what we get is actually the classical version back, and this is a positive, but this is just a sub-bundle maybe of the bundle we are really interested in. Yeah. Because we are interested in the twisting with a big one, and not with an ample one. Yeah, this is, and remember, so to wrap this up, so the trick was that we allow metric has the metric H has some zeros, and by this we could allow poles for the sections for the sections, and this gives us that we can plug in this E here, what was tensorizing by this D in the general formula. This was this is the reason why we get this E here in this formula, because the metric has zero, so we can allow for the L2 sections, we can allow poles. Okay, and yeah, that's so far that's it, and thanks for your attention.
Thank you very much. Thank you very much for this talk. Can you, are there any questions or remarks from the audience? Well, I do have some questions, actually. It's technically, when you apply this Tian-Yao result, the construction of Einstein matrix, do you need some kind of behavior of the metric? I mean, do you need this improvement that appeared later on the behavior of the metric close to the divisor? You know, or you just use the Monge-Ampère equation, basically the solver?
Yeah, you actually need some improvement. So in the form that I mean, first you need also to have some that it's varying depending smoothly on S, because it really should give a smooth metric on this relative canonical. And this involves already, also this was already done by Schumacher, so this involves applying the implicit function theorem to this CK alpha spaces with respect to quasi-coordinates. So
all the spaces introduced by actually,
by
Kobayashi and so on. Okay.
Yeah, this is where this is showing up at this point. Although it's hidden in this part, so to speak.
So I have a question. I imagine not much works in the log Calabi-Yau case instead of log canonically polarized case.
Yeah, it's. I think it should also go through. I think it's so the computation is. It's mostly analogous, I think, for the curvature. So it's. I think it's.
There is a difference there in the at least the let's say in the non-log in the usual Calabi-Yau families, that this Keller-Einstein metrics unfortunately do not have PSH variation in general. So that part you wouldn't have, but whatever didn't need that part probably can go.
You would get a curvature formula. I'm pretty sure. Yeah, you would get.
Okay, thank you.
Yeah.
So maybe I have a question.
Yeah.
So okay, so in your case, you always consider the fiber to be canonical polarized or log canonical polarized in order to get a Kerr-Einstein metric along the fiber, right?
Yeah,
But
yes,
but in generally, we do not have so nice situation. For instance, the fiber could be only the canonical line bound could be only semi-ample, or more generally, only have a good minimum order. This means that you do not have this kind of Kerr-Einstein metric. How can you do in this case?
So, so in my case, so this was, so to speak, the first step into this more singular situation that you allow for L just not ample, instead maybe bigness or something. So
yes.
So Poincaré type, this implied that something is neff and big. So this is it's a bit, so it's better than neff and big, yeah. But then there is so there's a more recent work by Berndtsson-Paun, where they give a curvature formula for I think more for the relative big case. So it's they don't, and so they allow for so-called what they call the generalized analytic singularities for their metric H, and they already in this case, so no really assumption on L on the curvature of L. I think it's just semi-positive, so just pseudo-effective. They get already a formula which is maybe not that intrinsic, and but this in the relative big case, they could improve this formula, and that they end up with some upper bound for the curvature expression, which consists just of the first integral here in this formula. So they end up with an upper bound for the curvature in the relatively big case. So maybe this goes in the direction of your question.